Welcome again. In this presentation, we will discuss some examples and properties of Fourier transform. We will discuss the Fourier transform of a moving average filter. We will study the symmetry of real valued signals. Let us now consider the Fourier transform of a moving average filter. This yn is obtained as 1/3 of un plus 1 plus un plus un minus 1. It uses the current value, the previous value and the next value. As n changes, the whole window shifts. So this is known as a moving average filter. It finds the average and the window itself moves. So it is known as a moving average filter. Recall the convolution expression. Now I would want to find the expression for g of k. The filter produces this output. The question I am asking is, what is the impulse response of the filter? That is given by Gn. So can I find Gn given this expression? So for that I expand it, g of minus 1 into u of n plus 1. Remember, when I add these two arguments I get this n, the argument rule, then g of 0 into u of n, then g of 1 into u of n minus 1. Why do I have only 3 terms here? Why not infinite number of terms? Because there are only 3 non-zero terms here. I get the corresponding 3 non-zero terms. So by matching the terms I get the expression for g of minus 1, g of 0 and g of 1. So what is g of minus 1? It is 1 by 3. What about g of 0? That is also 1 by 3, because 1 by 3 multiplies u of n. Similarly g of 1 is also 1 by 3. Okay. So now we have all the g's required to calculate Z transform. All other terms are 0. G is non-zero only for 3 entries, namely g of minus 1, g of 0 and g of 1. So let us evaluate g of exponential j omega. Okay. So let us evaluate g of exponential j omega, which is nothing but Z transform evaluated at z equals exponential j omega. So I have g of minus 1 is here, which is 1 by 3 into z power minus n. When I substitute z equals exponential j omega, I get exponential. Because it is minus 1, it becomes plus j omega, then 1 and then exponential minus j omega. It is easy for you to verify this, and when I simplify this it becomes 1/3 of 1 plus 2 into cos omega. Now let us write the magnitude and the phase of this. The phase is also written as argument of g. I would want you to verify that these two are indeed satisfied. For omega in the range 0 to 2 pi by 3, you get 0. Actually you get cos omega as minus 0.5, so they cancel each other, and beyond that you get pi. You can draw this in the familiar Bode plot, where I plot magnitude versus omega in the log scale. I have the Scilab code now in this page. Here is the transfer function capital G, and then I have the magnitude on the right hand side and the argument. Let me go to the Scilab window. I am already at the correct directory. Let me execute this. You get the Bode plot that I showed earlier. We will next consider the symmetry of real valued sequences. Recall the discrete time Fourier transform. Now I have the additional information that Gn is real, that the impulse response is real. Until now whatever we have discussed is applicable for complex g small g as well, but now we have the additional restriction that this g is a real valued sequence. This is what we expect in our control problems where we deal with real life systems. So as a result we expand only exponential term into sine and cosine. So we get this cos omega n term and then sin omega n term. Similarly, let us write exponential minus j omega. So wherever I have omega I have to replace it by minus, so I get plus j omega n here. When I expand it, the real term remains the same, but in imaginary I have plus sign. Remember, I am calling this as real because g is real. So I can separate this using only the cos and sine term that come from here. Okay. The imaginary term is contributed only by the sine term here, no contribution from here. So I can write it as real and imaginary. Similarly for exponential minus j omega, I have real and imaginary. So we conclude that the real part of g and g of exponential minus j omega are the same, whereas for imaginary you see a minus sign here. So imaginary of this is equal to minus imaginary of this expression. So the real is the same, imaginary has a minus sign. So we see that these two are complex conjugates, and so we have arrived at g of exponential j omega equals g star of exponential minus j omega. This star means complex conjugate, that means real part is the same, imaginary part is negative of each other. This is known as the symmetry of magnitude for real valued sequences, and the magnitude is nothing but the expression multiplied by its complex conjugate square root, or you can also do this using minus j omega. This is written as magnitude of g of exponential minus j omega or absolute. So you see that the magnitude of exponential j omega is nothing but magnitude of exponential minus j omega. Notice that these two are equal, these two are equal, so we get this expression. This shows that magnitude is an even function, that is when you replace g exponential j omega with exponential minus j omega, you get the same expression. It shows that the magnitude is an even function. Similarly, you can show the argument to be negative. Similarly, we see that the argument obeys this equality, where the argument of this expression is the minus of the argument of its complex conjugate, where we have replaced minus j omega with plus j omega here. This has an important implication for calculations. We need to draw Bode plots only for omega in the range 0 to pi, because magnitude is the same and phase is just the negative, so we do not need that. Both magnitude and phase for the range minus pi to 0 can easily be concluded from the Bode plot drawn in the range 0 to pi. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.